You think you know why water freezes. You've seen it happen 1,000 times. You put water in the freezer, it turns to ice. Temperature drops below 32 degrees Fahrenheit, liquid becomes solid. Simple, obvious, the kind of thing a child understands. But here's a question. What's actually happening? Not the temperature number, not the when, the what. When water freezes, what changes? You'll probably say the molecules slow down, they stop moving. They lock into place. Cold means slow, frozen means stopped. That's what everyone thinks. Wrong. The molecules in ice are not stopped. They're not locked in place like bricks in a wall. They're vibrating, constantly, furiously. Even at absolute zero, which you can never reach, quantum mechanics says they'd still be jiggling. At the temperature of ice in your freezer, those molecules are shaking back and forth thousands of times per second. So if the molecules are still moving, if they're still jiggling around, what's the difference between ice and water? Why is one rigid and the other flows? What actually changed? You can't answer that, can you? You thought freezing was about stopping, but nothing stopped. You thought it was about temperature, but temperature is just a number we assign to molecular motion. The real question is deeper. When water transforms from liquid to solid, when it crosses that boundary at 32 degrees, what physical process occurs? What mechanism drives that transformation? And why does it happen so suddenly? Why doesn't water gradually get thicker and thicker until it's solid? Why does it stay liquid, 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 then snap into ice? If you think the answer is just it gets cold, you're not thinking. You're just labeling the mystery with a different word. Let's start with what you think you know. Water is H2O, 2 hydrogens, 1 oxygen. You learned that in school. And you probably learned that when water is warm, the molecules move fast. When it's cold, they move slow. At freezing, they slow down enough to stick together into a crystal structure. Ice. Sounds reasonable. Feels right, and it's completely missing the point. Here's a simple experiment. Take a glass of water at room temperature. The molecules are moving around, bouncing off each other, flowing past each other. Now put it in the freezer. The temperature drops. 50 degrees, 40 degrees, 35 degrees. The molecules are moving slower now. Less kinetic energy. You'd expect them to pack closer together, right? Less motion means they can settle into a tighter arrangement. Things contract when they cool. That's normal. But watch what happens when the water hits 32 degrees. It freezes, and when it freezes, it expands. The ice takes up more space than the liquid water did. That's why ice floats. That's why water bottles explode in the freezer. That's why pipes burst in winter. The solid form is less dense than the liquid form. Stop. Think about that. The molecules slowed down, and the substance got bigger. That's backwards. That violates everything you thought you knew about cold and hot. When things get colder, they contract. Steel, copper, glass, air, everything shrinks when it cools. But water expands when it freezes. Why? Your simple explanation just died. Molecules slow down and stick together doesn't explain expansion. If they're sticking together, they should pack tighter, not spread out. So what's really happening? What's the mechanism that makes ice less dense than water? The answer is in the shape, not the shape of the molecules, the shape of the forces between them. Water molecules are not spheres. They're not simple balls bouncing around. A water molecule has a specific geometry. The oxygen atom sits in the middle. The 2 hydrogen atoms stick out at an angle, about 104.5 degrees apart. It looks like a Mickey Mouse head. Oxygen is the face, hydrogens are the ears. And here's the critical part. The oxygen side of the molecule has a slight negative charge. The hydrogen side has a slight positive charge. Not much. Not enough to make water an ionic compound like salt, but enough to matter. Enough to create what we call a polar molecule. One end is slightly positive, the other slightly negative. Now put a bunch of these polar molecules together. The positive end of one molecule is attracted to the negative end of another. Positive to negative, hydrogen to oxygen. These attractions are called hydrogen bonds. They're not as strong as the covalent bonds holding the H2O molecule together, but they're strong enough to influence how water molecules arrange themselves. In liquid water, the molecules are moving fast enough that these hydrogen bonds constantly break and reform. A molecule forms a bond with its neighbor, vibrates, breaks free, forms a bond with a different neighbor. The structure is chaotic, constantly changing. The molecules are close together because the motion keeps them bumping into each other, but there's no long-range order. It's a dense, disordered crowd. Now cool it down. The molecules move slower. They have less kinetic energy to break those hydrogen bonds. At some point, the energy of thermal motion drops below the energy of the hydrogen bonds. The bonds stop breaking. The molecules lock into a pattern. And here's where the geometry matters. Because of the angle of those hydrogen bonds, because of the specific shape of the water molecule, the most stable arrangement is not the most compact arrangement. When water molecules lock into a crystal structure, each oxygen atom bonds to 4 hydrogen atoms from neighboring molecules. 2 from its own hydrogens bonding to other oxygens, and 2 from other hydrogens bonding to its oxygen. 4 bonds arranged tetrahedrally, pointing to the corners of a pyramid. This tetrahedral arrangement forces the molecules apart. The structure has space in it, gaps, holes. The crystal lattice of ice is more open than the jumbled mess of liquid water. The molecules are actually farther apart on average in ice than they are in liquid water. That's why ice is less dense. That's why it floats. The expansion isn't random, it's geometric necessity. The hydrogen bonds have a preferred angle, a preferred length. When they all lock in simultaneously, they force the molecules into a structure that has more space than the liquid did. The molecules didn't stop moving. They're still vibrating, still jiggling in place, but they're jiggling within a rigid framework now. A framework held together by billions of hydrogen bonds, all pointing in the same directions. But we're not done. We haven't actually explained why it happens suddenly. We haven't explained the phase transition. Think about what has to occur for water to freeze. You have a glass of liquid water at 33 degrees. Every molecule is moving, bonding, breaking bonds, moving again. Chaos. Now you drop the temperature 1 degree to 32. Suddenly all the molecules lock into a crystal structure. Billions and billions of molecules, all making the transition essentially simultaneously. The entire glass of water transforms from liquid to solid in seconds. How? If each molecule independently decided when to join the crystal, the transition would be gradual. Some molecules would lock in first, others later. You'd get a slush, a mixture of solid and liquid that slowly shifted from mostly liquid to mostly solid over a range of temperatures. But that's not what happens. Water stays liquid right up to the freezing point, then transitions sharply. Why? The answer is nucleation and cooperative behavior. This is where it gets beautiful. A single molecule can't freeze by itself. Think about it. For a molecule to be in the solid state, it needs to be bonded to its neighbors in that rigid tetrahedral pattern. But if all its neighbors are still moving around in the liquid state, there's nothing to bond to. The molecule would form a bond, the neighbor would wiggle away, the bond would break. Trying to freeze one molecule in a sea of liquid doesn't work. You need a cluster. You need several molecules to lock together simultaneously. But here's the problem. Small clusters are unstable. Imagine 5 or 6 molecules trying to form a tiny ice crystal in the middle of liquid water. The molecules on the surface of that tiny crystal are being bombarded by liquid molecules. They're constantly hit with energy from the chaotic motion of the liquid. That energy breaks the bonds. The cluster falls apart. For a crystal to grow, it has to be big enough that the molecules in the interior are protected from the chaos of the liquid. Only at the freezing point does the math work out. Only at 32 degrees is the thermal energy low enough that a cluster of molecules, if it happens to form by chance, can survive long enough to grow. And once one cluster reaches that critical size, once you have a stable ice crystal nucleus, it grows explosively. Liquid molecules at the surface of the crystal have something to bond to now. They snap into place. They join the crystal. The crystal gets bigger. More surface area means more places for molecules to attach. The growth accelerates. Within seconds, the entire volume of water is converted to ice. This is a phase transition. It's not a gradual process. It's a runaway cascade. Once the conditions are right, once you have nucleation, the transformation happens fast. Liquid to solid, all at once, driven by the cooperative behavior of trillions of molecules, all locking into the same structure simultaneously. And here's something that should bother you. Where does that ice crystal nucleus come from in the first place? Pure water, absolutely pure, can be cooled below 32 degrees without freezing. This is called supercooling. You can get liquid water down to 20 degrees, 10 degrees, even lower if you're careful. The water wants to freeze. The temperature is right. But it can't, because there's no nucleus to start the process. The random thermal fluctuations in the liquid aren't forming clusters big enough to survive. Then you tap the container, or you drop in a speck of dust. or an ice crystal from somewhere else. Suddenly you have a nucleus, and the entire volume of supercooled water transforms to ice instantly. The transformation is so fast, so violent, that the water can freeze into bizarre shapes, into spikes, into formations that look impossible. In the real world, pure water is rare. There's always dust, always impurities, always something to serve as a nucleation site. That's why your ice cubes freeze at 32 degrees, not at 10 degrees. The nucleation sites are already there, but the principle remains. Freezing is not about gradual slowing. It's about critical thresholds and cooperative transitions. Now let's go deeper. Let's ask why hydrogen bonds exist in the first place. Why do water molecules have this polar structure? Why does the oxygen side have a negative charge and the hydrogen side a positive charge? The answer is electronegativity. Oxygen atoms pull electrons more strongly than hydrogen atoms do. When a hydrogen and an oxygen bond to form H2O, the electrons in that bond spend more time near the oxygen than near the hydrogen. Not all the time, not completely, but enough to create a slight imbalance. The oxygen gets a partial negative charge. The hydrogen gets a partial positive charge. This is quantum mechanics. Electrons are not little balls orbiting the nucleus. They're probability clouds. The cloud is denser where the electron is more likely to be found. In a water molecule, that cloud is skewed toward the oxygen. That skew creates the polarity, and polarity creates hydrogen bonding, and hydrogen bonding creates the structure of ice. And the structure of ice is why your ice cubes float in your drink. Follow the chain. Quantum mechanics determines electron distribution. Electron distribution determines molecular polarity. Polarity determines intermolecular forces. Intermolecular forces determines crystal structure. Crystal structure determines density. Density determines whether ice floats or sinks. It all connects. Every piece follows from the previous piece. There's no magic. There's no mysterious force of cold reaching in and solidifying things. There's just atoms, electrons, forces, and geometry. But here's where you need to think carefully. We've explained how water freezes. We've traced the mechanism from hydrogen bonds to crystal structure to phase transition. But we haven't explained why those particular quantum mechanical rules apply. Why does oxygen pull electrons more strongly than hydrogen? Why do electrons form probability clouds? Why does quantum mechanics work the way it does? And the answer is, we don't know. Or rather, we can describe it mathematically. We can write down the Schrödinger equation. We can calculate the electron distribution in a water molecule to extraordinary precision. We can predict every property of ice from first principles. But we can't tell you why the Schrödinger equation is the correct equation. We can't reduce it to something simpler. This is where physics hits bedrock. You can keep asking why, but eventually you reach fundamental laws. And fundamental means there's nothing underneath. The laws just are. They're what we measure. They're what the universe does. So when you ask why water freezes, the complete answer is this. Water freezes because at 32 degrees Fahrenheit, the thermal energy of molecular motion drops below the binding energy of hydrogen bonds, allowing molecules to lock into a tetrahedral crystal structure that is less dense than the liquid state. The transition happens suddenly because it requires cooperative nucleation and grows through a runaway cascade once a critical cluster size is reached. The hydrogen bonds exist because water molecules are polar due to the electronegativity difference between oxygen and hydrogen, which is a consequence of how electrons distribute themselves according to quantum mechanics. That's the answer. Not it gets cold, not molecules slow down. The real mechanism, the actual physics, the chain of causation from quantum mechanics to crystal structure to phase transition. But let me show you why this matters. Let me show you why this isn't just academic detail. The fact that ice floats, the fact that water expands when it freezes, this is the reason life on Earth exists. If ice were denser than water, if it sank instead of floated, lakes and oceans would freeze from the bottom up. In winter, ice would form at the bottom. It would be insulated by the liquid water above. It would accumulate. Season after season, year after year, more ice would pile up on the bottom, protected from the summer sun by the water above. Eventually, entire oceans would be solid ice with only a thin layer of liquid water on top. But because ice floats, because of that weird expansion driven by hydrogen bond geometry, ice forms at the surface. It creates an insulating layer that protects the liquid water below. Lakes freeze on top, but stay liquid at the bottom. Fish can survive the winter. The ice melts in the summer. The cycle continues. This one bizarre property of water, the fact that the solid is less dense than the liquid, is the reason aquatic ecosystems exist. It's the reason the oceans didn't freeze solid billions of years ago. It's the reason life had a place to evolve. And it's all because of the angle of a hydrogen bond. 104.5 degrees. That's the difference between a living planet and a frozen rock. You thought freezing was simple. Cold makes things solid. But the reality is extraordinary. Quantum mechanics determines molecular geometry. Geometry determines bonding angles. Bonding angles determine crystal structure. Crystal structure determines density. Density determines where ice forms. Where ice forms determines whether life can survive. Every time you drop an ice cube in your drink and watch it float, you're seeing quantum mechanics in action. You're seeing the geometry of hydrogen bonds. You're seeing the cooperative phase transition of trillions of molecules. You're seeing the reason your planet is alive. That's what freezing is. Not a simple process of things getting cold and stopping. A quantum mechanical, geometrically determined, cooperatively nucleated crystallization process that links the behavior of electrons to the survival of ecosystems. And you thought you understood ice. The next time you watch water freeze, the next time you see frost forming on a window or ice crystals growing in the freezer, remember what's actually happening. Billions of water molecules, each one a tiny dipole with a specific geometry, each one feeling the electromagnetic pull of its neighbors, all of them simultaneously, making the transition from chaotic liquid to ordered crystal. The hydrogen bonds snapping into place, the tetrahedral structure forcing the molecules apart, the density decreasing even as the rigidity increases. You're not watching water get cold. You're watching the fundamental forces of nature expressing themselves through geometry and statistics. You're watching quantum mechanics become visible to the naked eye. This is what physics offers. Not comfortable stories about things slowing down and stopping, but precise mechanistic explanations that connect the smallest scales to the largest consequences, from electron orbitals to planetary habitability, from bond angles to the existence of life. The universe doesn't care whether the explanation makes you comfortable. It doesn't care whether it matches your intuition. The universe just is. Water freezes the way it freezes because of the shape of its molecules and the strength of its bonds. That's the truth. That's reality. And reality, when you actually understand it, when you see the connections and the mechanisms and the inevitability of it all, is more beautiful than any comfortable lie. That's not mysterious. That's magnificent.